Believe in yourself, for that's the place to start. And I say, hey, what a wonderful kind of day, if we can learn to work.
Okay, everyone, welcome back to another video. And so in today's video, we are going to discuss in 5 minutes or less, as a goal, the concept of simultaneous measurement, right? And this is it's not a hard problem, but it's a problem I've been obsessed with for far too long, right? And I'm finally getting some papers out on it. But so essentially, the idea comes from the concept of what can I know given a single measurement, right? And it sounds like if you ever taken a quantum mechanics course, this is a question that I feel needs to be answered way more often than has ever been brought up, right? You touch on it a little bit because you deal with the commutator relationship all the time in quantum mechanics, but you don't really dive into what it really means, right? So essentially, what a commutator relationship means, or we say two observables commute in quantum mechanics, what that tells you is you can simultaneously know both those values. So um, the way I like to phrase it is, if I measure A first, then B, it's no different than if I measure B first, then A. That's how I view what the commutator relationship is telling you. So you probably have heard, if you are a fan of science, and I assume you're a fan of science if you're watching this video, of Heisenberg's uncertainty principle. And essentially, what Heisenberg's uncertainty principle is hitting the nail on the head of what the commutator relationship is about. It's saying if I measure position, then momentum, I will necessarily get a different result than if I measure momentum, then position. There's always going to be an uncertainty between knowing both at the same time. In other words, you can't know them at the same time because their measurements um, change the value of the other observable, right? Now, what is very cool then is to ask the following question: how much information can I know about my system given a single measurement? And so in quantum mechanics, what this means is, now we're going to get a little more mathy, we're going to get a little more sciencey here, is your system before a measurement occurs exists in what is known as a superposition or a linear combination of your states. So what that means is, my favorite one is electron spin, right? So we say electron spin before measurement occurs, right? Before measurement occurs, and all the measurement for electron spin is this permanent magnet in a screen, right? And so what happens as this electron, or I guess this atom in this case, flies through this permanent magnetic field, it gets pushed up or down, right? And it only gets pushed up or down into these two values, right? It either could be a spin up or spin down, right? So we say before a measurement occurs, you're in a superposition of being both spin up and spin down at the same time. Or mathematically, we write this as a linear combination. So mathematically, let's see if I can pull this up here real fast. Um, do, 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 do. Let me see. How do I do this? Order, move up. Okay, can't do it. Um, Either way, it's just an addition property of quantum mechanics. And so what happens when a measurement occurs, we have this axiom or this rule that says once a measurement occurs, your state is then projected into either spin up or spin down. This is also known as collapse, right? So your state goes from being both of them to just one or the other, right? And then you lose information associated with the other one, and now let's just say it's spin down. So for all time until another measurement occurs, that state is known as being spin down. Um, so now we know what happens, right? But think of the reverse problem now. So I measured spin, and now my state has projected into on that axis into a state of spin down, right? But what happens when that measurement occurs to the observables that do not commute with spin, right? So, for example, in quantum mechanics, it is known that if you measure spin on the z-axis, for example, so we have a measurement device on this axis, and then we have a measurement device, let's say, on the x-axis, right? The spin on the x-axis is going to go back into a general state. It's going to go back into that superposition or that linear combination of being spin up and spin down, right? So, and not only on the x-axis, but also on the y-axis. So a single measurement caused three projections in the spin case, right? One projection gave us a definite value of being spin down, but two other projections turned it back into a general state. And so, what we will be exploring in the upcoming videos is exactly what happens to those states not chosen. How does the universe look from their point of view, essentially? How does the universe handle the transition from being, in a known state to constantly being into unknown states? And finally, we will rule and calculate how many how many observables commute with certain observables, and how many of them don't commute with certain observables, and what that means in general. So it will be a fun week, and stay tuned for more videos.